This is the lecture for Friday, February 7th. We will be talking about nuclear sizes. We already started this lecture on Wednesday, but I would like to just back up to the beginning of the lecture. So we can probe the structure of a nucleus. How big is it? What is its radius, or its root mean square radius, by doing scattering experiments. For example, we can have an electron being shot into some nucleus that scatters against the nucleus, and the electron deflects by some angle theta. And then you can measure the cross-section for the scattering process as a function of the angle theta, the deflection angle theta. And there's a very simple formula by Rutherford that explains what this should look like for Coulomb scattering between two particles that are interacting through the Coulomb repulsion, where one of the particles is sufficiently heavy that it doesn't recoil. And the formula looks something like this. It's proportional to the fine structure constant alpha squared, is proportional to z squared, and then there's a factor of 1 over the kinetic energy of the electrons squared, and a factor of 1 over 1 minus cosine of theta quantity squared. Now, if we put in the corrections due to the electron, the real electron properties, the fact that they have spin, they have relativistic properties, they have magnetic moments, and that the fact that the nucleus does recoil, it doesn't have infinite mass, then we get a more realistic Mott cross-section. So the Mott cross-section looks very similar to the Rutherford cross-section when the angle is close to 0. So here's a plot of the cross-section for Rutherford versus the Mott scattering. And you can see that they're quite similar here. But when the angle is closer to 180 degrees, they're quite different. Now, when Hofstadter did his electron scattering experiment, he saw that there was actually quite a bit of a deviation from actually both of these predictions. That was indicating that the nucleus actually had quite a bit of structure to it if you probe it at sufficient high enough energies. So one way to quantify the structure of this nucleus is to take the cross-section that you measure and divide it by the point structureless cross-section given by the Mott cross-section formula, and the extra piece left over is what's called the form factor. This f function, the form factor actually squared, absolute value squared, f of q quantity squared, where q is the momentum transfer, the magnitude of the momentum transfer. So q3 vector, qx, qy, qz are the components of the amount of momentum that the electron gives to the nucleus, that it kicks to the nucleus. Now this form factor f of q is related to the charge density of the nucleus, rho, charge density of r, okay, just rho of r. But you have to Fourier transform this into momentum space. So if I take the charge density, take the Fourier transform by multiplying by e to the I q dot r, and then integrating over d3r, then I get the form factor. So what does this charge density look like? Well, first of all, I should mention, from the experiment, you can get a measure then of the charge density. But what does this charge density of the nucleus look like? Well, it looks something like this generically. You have, there's some central density that we call rho sub 0. And so for larger nuclei, this actually is a rather well-known value. It's about 0.16 nucleons per cubic femtometer. Now, then there's some flat central region here, or relatively flat central region, depending on the nucleus. And then there's a point at which the density drops over this sort of interval, which is called it's called diffusivity. This region where it drops from its maximum to near to its minimum. And a rather simple prescription, empirical relation for the density profile is given by this formula, what's called the Woods-Saxon potential. Woods-Saxon, two different people. And So it's rho 0 times this function that's 1 over 1 plus the exponential of r minus capital R over a. So as you can see here, at r is equal, when r is equal to capital R, that's when we are passing through the place where the argument of the exponent goes to 0. Okay, and so that's where this guy changes quite a bit. So this capital R determines where this function goes from a large value to a small value. Now, if R is very large, then what will happen is that we notice that then this exponential becomes very large because you get a large positive exponential, but it's in the denominator, so it's actually a decaying exponential function. That's why you get this tail to it. Now, when r is very small, then what happens is that this small r can be neglected, and you only get the contribution from this exponential minus capital R over a, and so it flattens out like this. So this capital R, the size of the nucleus, empirically you can determine that it scales like the third power, the third root of the number of nucleons. That's not too surprising because the nucleus has some quasi sort of spherical shape to it, and you can imagine filling this little sphere with nucleons, and so the radius of the nucleus will then be proportional to a to the 1/3 power, because the number of nucleons will be proportional to r to the third power. Okay. Now, so then this parameter here, just empirically, a is about, the small a is about 0.6 femtometers. Fermi is an abbreviation for femtometers. Okay, this is a close-up of the densities, the charge densities for various nuclei. You can see for helium-4, it's a rather compact object with 4 nucleons. And so for carbon-12, you see there's it's a bit wider. There's a little bit of a dip here, suggesting there might be a little bit of a hole at the center of carbon-12. That you can actually explain if the carbon-12 actually had sort of an alpha cluster structure to it, where you have 4 nucleons forming something that looks like a helium nucleus, an alpha particle, another 4 over here, another 4 over here. If this is your carbon-12, then you would naturally have a little bit of a dip at the center, which you see here. Now then you have your calcium-40, okay, and then you have your calcium-48, your nickel 56, and then you have your tin-124 and your lead-208. Right, you can see the comparison between an experiment, the solid lines, and a mean field calculation, where you treat you make a simplification where there's an effective interaction of all the nucleons that each nucleon then individually feels. So it's sort of like saying, I have lots of nucleons, there's an average potential that the nucleons are feeling, so you can replace that by some sort of a mean potential, and then solve for the density of nucleons that you get from solving that very simplified picture of this mean field approach. Okay, now the protons and neutrons, though, are themselves not point particles, so you can actually measure the charge distribution of the neutron by doing electron scattering again. And so what you see is that it seems to be that the positive, well, I should mention, so the neutron, if you think in terms of quark levels, the simplest quark structure, there's an up quark which has a positive 2-phase charge, and then there's a down quark that has negative 1/3 charge, another down quark that has a negative 1/3 charge. Since there's 2 down quarks, it turns out, because there's 2 of them, there tends to be more negative charge away from the center than there is positive charge, so that's why you see a positive distribution and then a negative distribution. Now, if you do it for the protons, though, you see that now for the protons you have plus 2/3 charge, and negative 1/3 charge, and so then you just see a positive distribution. Now, if you were to measure the charge distribution of a nucleus, then you can compute the charge distribution of a nucleus in terms of the point proton charge distribution, making the approximation that the protons themselves have no size to them, and just measuring them what is the distribution of all these point-like protons in a nucleus. But then what you can do is you can add in the fact that each individual protons have some size to them, and add this into the square of the radius. So what we're doing is we're adding the squares together, because you can think of these as uncorrelated sort of distributions. So you add squares of observable quantities like these together. So you have the charge radius for the proton, you have the charge radius to the neutron. Now it turns out the charge radius to the neutron ends up being negative because the negative charges are at larger radii than the protons. And then there's also a correction that you get from relativistic corrections called the Darwin-Folded correction. Now, it was believed that the charge radius for the proton, so this is what's called the RMS radius, the root mean square radius, where you measure the average value of the radius squared, and then you take the square root of that answer. So the root mean square radius the proton was believed to be 0.8775 plus or minus 0.0051 femtometers. That was for quite a while. However, recently there was realized that this does not seem to be completely consistent. Okay. But however, let me tell you the situation from doing various different types of experiments. So there were data coming from various different. There's a whole bunch of different experiments being listed here. As you can see, there's some sort of convergence of an answer somewhere in this region, about 0.88 femtometers. And similarly, if you look at what the proton charge radius just obtained through hydrogen spectroscopy, that is to say, you have your hydrogen, which is a proton, and then you have the electron here. And so what you do here, I'm going to actually explain this a little bit more on the next slide, but you can actually detect the charge radius of this proton by looking at small differences in the energy of the electron as in an orbital around the proton. There's a small dependence on the charge radius to these energies. So then you can measure these shifts, the energy differences between different orbitals as the electron drops from one orbital to another. And you can measure this very precisely because you can measure the light that's produced. And then that will give you sensitivity to the charge radius of the proton. And so it looks like the value is about 0.88 or so, 0.87, 0.88. Okay. However, there was then a measurement done that seems to blow all this away. Okay. There was a new measurement of the proton that was done in 2011. There's a famous paper in Nature by Randolph Pohl and company, and they made a measurement and found a value of 0.84087 with a very, very small error of 0.00039. They did this experiment, though, by replacing the electron by a muon, so they did a heavier version of this hydrogen atom. And because this muon is about 200 times heavier than that of a proton, it actually ends up sitting closer to the proton. And because it sits closer to the proton, the energy levels for the muon, which is called muonic hydrogen, those energy levels are much more sensitive to the radius of the finite radius, the non-zero radius of the proton. And so that's why they were able to, by doing the spectroscopy for muonic hydrogen, they were able to get a very precise measurement for the proton. However, this was a big controversy because this is completely in disagreement with the previous measurements. I'll say a little bit more about that later. Now, this same group then also measured the charge radius of the deuteron, and they actually found a result that's consistent with their own measurements of the radius of the proton and inconsistent with, so there's essentially a very simple explanation that they are consistently measuring the fact that the radius of the proton is smaller than what was believed to be, and then the radius of the deuteron, which is a proton plus a neutron in the bound state, we discussed this before, the the size of the deuteron was proportionally smaller because of the fact that the proton had a smaller charge radius. Now here's a little comment here that very often these funny discrepancies are due to the fact that people sometimes are more confident in a measurement because they get the same result as somebody else has gotten, and they are maybe thinking that well, maybe I should say it this way, they may be a little bit hesitant to publish a result that's in disagreement with an existing measurement, and so there's a tendency for a value to be accepted, and then all of a sudden somebody's brave enough to do another experiment that disagrees, then it plateaus to one value, and then it plateaus to another value, and it plateaus to another value. You see there's some sort of correlation between successive experiments until somebody figures out that maybe this result was wrong. Okay, so this is for the neutron lifetime, and I should mention there's also still some disagreement on what the neutron lifetime is. I mentioned in class that there are different ways of measuring the neutron lifetime. And then here's another example of measuring the mass of a particle called an eta meson. And again, here there was one value, then it went to another value, now we seem to have converged to a different value. So this is maybe perhaps what has been happening with the proton radius. Okay, but that still needs to be completely resolved yet. Now, there are some experiments of the charge radii of nuclei that are still, the issue of the proton radius is unresolved, but you can measure the change in the charge radius of a nucleus as you add more neutrons. So remember the term isotope is you have a given nucleus with a certain number of protons, z protons, and let's say it has n neutrons. If you keep z fixed but you increase n or decrease n, you're probing different isotopes. So as you change the number of neutrons, you aren't changing the Coulomb field of the nucleus. That's only determined by the number of protons. So as a result, the electronic structure of the different isotopes is almost exactly the same. Now, if you then add some extra neutrons or take away some neutrons, you can measure small differences in the energy levels of the electrons, of the electronic orbitals. And so that's what's called the isotope shift. And now, in order to do these precise measurements and analyze the changes, you have to then go through all these very small corrections that could occur to be able to extract out the change that's coming from the different nuclear structure. So what this is measuring now is the change in the charge radius of a given nucleus as you keep z fixed, but you increase the number of neutrons. Okay? And generally what happens is that the charge radius increases. You can think of as the neutrons are sort of allowing the charge to expand out a bit. Even though the neutrons themselves are chargeless, they allow the charge to spread out a little bit more. Okay, so here is the difference in the charge rate, the RMS radius, the charge radius. This is for different elements. So you can see krypton, rubidium, and so on, as a function of the number of neutrons. Now here's some work done at NSCL on measuring this change in the charge radius, the relative change in the charge radius for iron, for magnesium, manganese, for calcium, and so on. And you can see the comparison then with various theoretical calculations. This is also another work that was done at NSCL, led by Kandu and Yosono, where they measured the charge radius of iron 52, 54, 56. And interestingly enough, there's actually a little dip here that happens in the charge radius that's associated with the closure of closure of a shell for the neutrons. This is something we'll discuss when we talk about the shell model. Okay. And then here's another work also involving a lot of people at NSCL, at the laboratory. And here is a comparison of, so this is for calcium, this is calcium. This work is about the increase in the charge radius
of calcium as you increase the number of neutrons. So this is the difference between the charge radii for calcium-52 and calcium-48. And so you can see the experiment got a rather large value, and you can see the various theories and what they predict. Here's from shell model calculation, which is not doing all that well, actually. Here's some density functional calculations, and here's some ab initio calculations, which was the focus of this particular work in Nature Physics. Now, we can also try to measure the neutron radius. So you can think of the charge radius as measuring the proton distribution of the nucleus, but the neutrons, which are neutral, are not really participating directly in terms of determining the charge distribution. So you can ask, what is a neutron distribution? Okay, so you can try to get that information by doing elastic scattering of a proton with the nucleus. You can try to scatter other things like pions, alpha particles, deuterons even. And then another thing you can do is you can actually shine photons onto the nucleus and look for the production of neutral pions that come out. It turns out that actually is going to give you some measure of the density of neutrons. However, all these probes are rather complicated. In other words, you get a nice experimental result, but the theoretical interpretation of what this means for the neutron distribution in the nucleus is a little bit difficult. So one way to try to access this is to use the weak interactions, which are a very clean probe. They are even weaker than the electromagnetic interactions. So what are the weak interactions that I'm talking about here? Well, the electron can scatter by spitting out a virtual photon that strikes this nucleus, but it also can spit out, this electron can spit out what's called a Z particle, a Z boson, or it's one of these bosons, vector bosons that mediate the weak interactions. This one happens to be the Z, which is chargeless, and the mass of the Z particle is much heavier than that of the proton. In fact, it's like it's almost 100 times or 90 some times greater than the mass of the proton. Now, what the weak interactions do, though, is that they violate parity, meaning that a mirror image flip where you would have left-handed particles flip into right-handed particles, this is being violated. So what you can do is you can measure some parity violating asymmetry scattering experiment where you flip the helicity, the spin, along the direction of motion of the electron. So you measure right-handed minus left-handed cross-section divided by the cross-section for right-handed plus left-handed. And you get then this result where you get contributions from the photon, and you also get the contribution from the Z boson. Now, so here's this Fermi constant here, GF, that's measures the strength of the coupling of the weak interactions, and this is a very small constant, which is the reason why, well, this is an indication of the fact that the weak interactions are very small, and so you can see this 7 times 10 to the minus 7th factor that comes about. Now, it turns out, though, that when you do the scattering, you can have the Z boson, either it can strike a proton in the nucleus, or it can strike a neutron that's in the nucleus. But it so happens, though, that because of an actual numerical accident, there's a cancellation between the terms that for the proton. And there's something called the Weinberg angle, which is, we will talk about this, all this stuff we'll be talking about towards the later half of the course. But there's something called the Weinberg angle that just so happens to have a value such that the sine squared of the Weinberg angle is about 0.23. So when you do 1 minus 4 times 0.23, you get something close to, well, you get something quite small. And so the weak interaction, the Z coupling to the proton here, will actually be suppressed for the proton. It'll be much stronger for the neutron. So this actually happens to be a nice probe of the neutron, if you can see this at all. What I mean is the fact that the weak interactions are so weak. Now, so let me make a comment about these weak interactions. If you have a weak interaction where you have the exchange of some particle which has a mass mz, so this is the Z particle, but it has a mass mz. This particle has a limited range to it. In fact, the range of this interaction, you can think of this as being associated with an exponential fall off, where mu is given by is proportional to the mass of the particle. Let's say just the mass of the particle. And so it turns out then that this z particle, this interaction, really can only propagate, or it can only exist for a very short distance. We will actually come back to this when we talk about the strong force a little bit later. We'll talk about this in connection with the pion particle as you kind of force exchange particle. Now, there has been a collaboration called the P-REX experiment. This is the proton radius experiment. Okay. There's also a C-REX experiment for the calcium radius experiment. And nowadays there's a P-REX2, which is the next generation P-REX experiment. This is all being done at Jefferson Laboratory in Newport News, Virginia. And so they're doing this experiment that we've been talking about, where you scatter the electron and look for parity-violating effects when it scatters off a nucleus like this. And you try to measure the properties of the weak interaction, and that gives us information about the neutron distribution. So what they're trying to measure is what's called the neutron skin. That is, what is the RMS, so the root mean square radius of the neutron, minus the root mean square radius of the proton, of that difference. So they've completed the first P-REX experiment. They came up with a result which is actually a little bit disappointing because the error bars are so large. They got 0.34 plus an error bar on the plus side of 0.15 and on the minus side of 0.17. Okay. Whereas theoretical results seem to suggest a value of about 0.17. So we're still waiting for a better measurement of this. I should mention, here's a nice picture of what the densities might look like for the neutron, for the proton. And so you're trying to measure the small differences in the fact that there's a little bit of a skin here. And so the neutron has a larger radius, RMS radius, than the proton does. Okay. And so now, if you have, however, a system where you have lots of extra neutrons, you might have then a halo sort of atmosphere to the nucleus where you have lots of extra neutrons, and you might have a much larger neutron radius or neutron skin. This, for example, this 10^150. Now here is now a plot of the expected neutron skin from a theoretical calculation for a nuclear chart, across the nuclear chart for neutron number here and proton number here. And you can see the neutron skin color-coded. You get larger neutron skins out over here, okay, as you might expect. And this is these are calculations done with a given density functional calculation. This HFB stands for Hartree-Fock-Bogoliubov. That's a particular way of doing some mean field calculations. And this is a specific type of an interaction form that's being used, SLY4. So, thanks for listening. I'll see you guys on Monday.